Hi, my name is Patricio Vasquez, and I will talk about the methodology that we use in our project. First of all, we describe the physical characteristic of the robot, including the wheel radius, the axle length, and the basic mobility constraints. These parameters are essential because they define how the rotation of each wheel translates into motion on the XY plane. Next, we apply the kinematic model of a differential robot. Using the standard equations, we relate the linear and angular velocity of each robot to the angular speeds of each wheel. After that, we implement the kinematic equation directly in MATLAB. The code was organized into blocks. We first configure the motor and reset the encoders, and then we calculate the wheel speeds required for each commanded motion. Finally, we defined the desired trajectory. In our case, was simplified five-shape figure. To achieve this path, we program 5 movement phases, 2 stretch segments, 2 90-degree rotations, and finally a curve motion. By recording the robots both through the execution, we were able to reconstruct and plot the entire trajectory in MATLAB. This methodology integrates the physical model, the MATLAB implementation, and all the real encoder data to evaluate each stage of the robot motion. Thanks.
Well, the results. We have some points. First, the robot successfully executed the file-shared path in the real world. This was achieved using MATLAB and the robot schematic model. The Lego robot correctly followed the planned strain segments. Second, the trajectory reconstructed through the odometry was less accurate. Although the physical movement matched the index shape, the odometry base plot show distortion, especially during transition between motion segments. And the last point is the small errors accumulate for limitation of normal odometry. Different factors such as wheel slip and encoder resolution caused radar pose estimation drift, resulting in a plotted path that differs slightly from the ideal trajectory. Then we have analysis. The first point is that there is a clean difference between physical motion and odometry-based estimation. The robot moved correctly, but the trajectory reconstructed from the encoder data show distortions demonstrating that odometry alone is not fully reliable. Second point is that odometry errors arise from factors such as wheel slip and encoder resolution. This means that wheel slip creates no systematic errors during turns, while low encoder resolution leads to quantization effects. Both contribute to accumulate drift and inaccurate the estimated path. And last point is that several strategies can improve odometry performance. This can be improved in changing mechanical precision using smoothed motion strategies like gradual curves and integrating additional sensors like a MPU 6050, reduce odometry drift and improve pose estimation.
I am Mario Viteri, and I'll talk about conclusions and recommendations. We have 3 main conclusions. The first one is that we can prove the mathematical model in order to program desired trajectories of the robot. The second one is that we could use MATLAB plotting tools to visualize clearly the resultant trajectory, meaning that we can easily identify errors or deviations on the trajectories. And the last one is that this practice successfully integrated an encoder readings and computation of the robot's odometric trajectory in real time, which provide us with the results that we later analyzed. And as recommendations, we have that it's desired to be done this practice in a controlled environment. This means in an optimal surface that prevents slippery for example, and also that it's recommended that we are as accurate as possible with the measurings of the distance of the robot to prevent any errors on the model. We were group 5. Thank you for your attention.